Over the last few lectures, we have been describing the problem of solving the Schrödinger equation, the time-independent Schrödinger equation, for a particle in a central potential. We had first described how to solve the angular equation and discussed various subtle points in connection with that. And from the last lecture, we have been talking about the radial equation. In the last lecture in particular, we talked about the radial equation for two very simple systems, the infinite spherical well and a finite spherical well. In this lecture, we are going to start by talking about a very familiar and simple system, one which we have solved in great detail in one dimension. We are, of course, talking about the three-dimensional version for that. This is the 3D harmonic oscillator, where the potential energy function is given by half m omega square r square. Because r square is x square plus y square plus z square, an alternative form for that particular potential is the one written here. As you can see, this potential energy term here is a sum of three distinct and functionally identical forms, one for each coordinate, and that actually ensures that you can easily solve this problem in Cartesian coordinates as well. But before we go there, let me just describe to you quickly what the Schrödinger equation is going to be. That, of course, is going to be Laplacian psi plus twice m by h cross square e minus half m omega square r square psi. And rather than solve it in polar coordinates, we can solve it in Cartesian coordinates. Simply by writing out the Laplacian in full, this is the form the equation takes. And now what we can always do is we can try separating out the problem by using the separation ansatz, that is, by writing the wave function psi, which is a function of x, y, and z, as a product of psi x times psi y, which depends only on y, times psi z, which depends only on z. And if you plug this into this equation up here and follow the standard procedure for separation of variables, it's very easy to see that this equation will split into three independent equations, one each for x, y, and z, and the three equations will look almost identical, except that the energy parameter in each will be Ex, Ey, and Ez respectively, and of course the coordinate will be x square, y square, z square, and the dependent variable will be psi x, psi y, and psi z. The connection between these three separation constants Ex, Ey, Ez and the energy parameter in the Schrödinger equation is easily seen to be just this. So here basically what you have are three independent harmonic oscillators, three independent one-dimensional harmonic oscillators, one for each dimension, and the total energy of the harmonic oscillator is actually a sum of these three independent harmonic oscillators. And this energy therefore simply works out to be h cross omega times nx plus half plus ny plus half plus nz plus half. Here we have just used the standard result that we know for the one-dimensional harmonic oscillator. And so the final result is, the energy for the three-dimensional harmonic oscillator is h cross omega times nx plus ny plus nz plus 3 by 2. Here, of course, nx, ny, and nz are quantum numbers which should be familiar from their version that we met while we were discussing the one-dimensional harmonic oscillator. There, of course, you had only one quantum number, n, for the oscillator. Here, effectively, we have three independent harmonic oscillators, and that's why we have three quantum numbers. These numbers can take values 0, 1, 2, 3, and so on, and it is the sum of these three values, nx, ny, and nz, which actually dictate what the energy is like. So the energy depends on the sum of nx plus ny plus nz. The wave function, on the other hand, depends on the values of nx, ny, and z. Now this leads us to one major difference between the three-dimensional case that we are considering now and the one-dimensional harmonic oscillator that we had discussed earlier. As we have seen, when we were discussing the one-dimensional harmonic oscillator, the energy levels were all non-degenerate. In fact, we had proven a general result that for 1D bound states there can be no degeneracy. In the present case, however, the situation is quite different. After all, as I said, the energy depends on the sum of nx, ny and nz, whereas the wave function depends on the individual values of nx, ny, nz. So there are several possible sets of nx, ny, nz which add up to the same number and gives rise to the same energy. So we have different wave functions, functionally independent wave functions, giving rise to the same overall energy. Now the ground state, the lowest energy state that you can have, corresponds obviously to the lowest possible values of nx, ny and nz, that is 0 for each, and this state is non-degenerate. The ground state energy, as you can easily see from this expression, is 3 by 2 h cross omega. So that's thrice as much as the one that you had for the one-dimensional harmonic oscillator. But the factor of 3 should not come as a surprise. You are really talking of 3 independent harmonic oscillator, one for each dimension after all. On the other hand, whereas the ground state energy, which is 3 by 2 h cross omega, is non-degenerate, so degree of degeneracy is just 1, the next one, 5 by 2 h cross omega, is obtained when nx plus ny plus nz is equal to 1. This can happen when any one of them, nx, ny or nz, is equal to 1. So there are 3 different ways in which this can happen, and the degeneracy for this is 3. 7 by 2 h cross omega, of course, for that nx plus ny plus nz has to add up to 2, and that can happen either if any one of the 3 is 2, so 2, 0, 0, 0, 2, 0, 0, 0, 2, or 2 of them are 1 and the third one is 0. Again, there are 3 different ways of doing that. So a total of 6 different possible combinations of nx, ny and nz give you the same energy E. So degree of degeneracy here depends on the energy level, and as can be easily guessed, higher energy levels have a higher degree of degeneracy. The connection between the two is something we are going to explore after we handle the same problem using spherical polar coordinates. Let us now discuss the solution of the same problem using spherical polar coordinates. And as we have already discussed in general, for the spherical polar coordinate solution for the Schrodinger equation of a particle in a central potential, the wave function can always be written down as a product of a radial part and an angular part y, and we have already discussed earlier that the angular part essentially is described by quantum numbers L and ml. L can take values 0, 1, 2, 3 and so on. ml for each specific L runs from minus L to plus L, 2L plus 1 values in all. And the specific functions of theta and phi, which describe the angular part, are called the spherical harmonics labeled y, L, ml, theta, phi. The radial equation, on the other hand, is characterized by 2 quantities. L actually enters into the radial equation through a centrifugal potential barrier term, L into L plus 1 h cross square by twice mr square. And of course, it's characterized by the energy E, which comes as an eigenvalue for this particular equation. The radial equation, which should be pretty familiar by now, is of this form: d2 capital R dr2 plus 2 by R d capital R dr plus twice m by h cross square E minus the potential energy, which in this case is half m omega square r square, minus an additional term called the centrifugal potential barrier. And let me just remind you that the potential energy and this additional term together is called the effective potential. And this helps us to essentially describe the same problem as if it were a one-dimensional problem. Now, this is really quite similar to the Schrodinger equation that we solved for the harmonic oscillator in one dimension. Of course, there are some extra terms here, like the 2 by R d capital R dr term, and perhaps even more importantly, the L into L plus 1 h cross square by 2m r square term. As we will see, the effect of these terms will be quite important in deciding the kind of solutions this equation has. Now, we will do something very similar to what we did for the one-dimensional harmonic oscillator. We will go over from R, which is dimensional, to a dimensionless variable rho, which will help us to simplify the equation, at least getting rid of some of the parameters that are sitting there. And with the standard, at least by now, hopefully standard, abbreviation lambda equals twice e by h cross omega, it's pretty easy to see that the equation will ultimately take this form. It will take a bit of algebra to go from this equation to here, but since we have already described that kind of algebra in great detail for the harmonic oscillator in one dimension, we are not going to repeat the same explanations once again. So this equation is a second order linear differential equation, and as always, our major aim or major goal at the very beginning should be to know our enemy properly, that is, know all the singular points of this equation rather thoroughly. One singular point which takes a bit of work to figure out, but it's actually something which should not come as a surprise because we have already seen that in the one-dimensional case, is that this equation has an essential singularity at very large values of rho. In fact, at rho goes to infinity. In addition, there's one singularity which is new to the 3D case. This equation has a regular singularity at rho equals 0. Remember what we said was the rho equal to 0 point, which of course is the r equal to 0 point, is bound to give us trouble because of the fact that the coordinate system is bad at r equal to 0. For spherical polar coordinates, the one-to-one connection between coordinates and the points breaks down on the axis, but breaks down even much more badly at the origin, because at the origin, the moment you say r equal to 0, theta and phi can be given any arbitrary value whatsoever, you end up with the same point. So infinitely many different values of the coordinates r, theta, phi actually all point to the same point. As a result, the coordinates are singular there, and we do expect problems at r equal to 0. And the kind of problem that you can see here is that the equation ends up having a singularity, and as a result, it will give you solutions which will behave badly at r equal to 0. Since r equal to 0 or rho equal to 0 in the dimensionless units happens to be a regular singular point, we expect the problem not to be that difficult to handle, and that will turn out to be the case. As in the case of the one-dimensional harmonic oscillator, it's actually the singularity at rho equal to infinity, which is the essential singularity, that is the one which really should bother us more. However, we have already learned how to handle that. We can figure out the asymptotic behavior of the function capital R of rho as rho goes to infinity from the equation itself. Once again, I'm not going to repeat the details of this because the details are essentially the same as the way in which we handled the case for the one-dimensional harmonic oscillator. You can easily find out from the equation itself that the behavior of R of rho as rho goes to infinity can be either like e to the minus rho square by 2 or e to the plus rho square by 2. And because we like the e to the minus rho square by 2 behavior much better than e to the plus rho square by 2 behavior, what we are going to do is we are going to write R of rho as e to the minus rho square by 2 times a function of rho and try to solve the resulting equation for capital F of rho. But let me just give you a word of warning here. Again, this should be pretty familiar to all of you. This capital F of rho may actually diverge as rho goes to infinity. In fact, may behave as badly as e to the plus rho square. In fact, you know exactly that if it behaves badly, it has to behave badly like e to the plus rho square, because we know the divergent behavior of R of rho could be e to the plus rho square by 2. So this is a possibility that we always have to guard against. Now, once you carry out this substitution, the equation that was originally of this form for capital R turns out to have this particular form for capital F. Again, it's a matter of simple algebra to go from this equation to this one. Now, is the equation for capital F any improvement over the equation for capital R? At first sight, it may even look like this equation is a bit more complicated than this one. Or at least they may look equally complex. But just to point out, if we were trying to handle the singularity at infinity, it would be great if the power series solution that you have can be sort of handled properly. In particular, if necessary, can be truncated. And for that, having a two-term recursion relation will be very, very good. Let's take a look at what happens if you tried the power series solution for the first equation. Term with rho to the n would end up giving you rho to the n minus 2 here. This one will also give you rho to the n minus 2. This term will also give you rho to the n minus 2. This term will give you rho to the n. But this term will give you rho to the n plus 2. So there are three different powers which will multiply Cn in this equation. And if you try to bring the powers of rho to the same value, this will give you a relationship between Cn plus 2, Cn and Cn minus 2. So you will end up with a three-term recursion relation. Not the best of things when you have to handle a potential divergence at infinity. What about the other equation, the equation for capital F? This would give you rho to the n minus 2. This one will give you rho to the n. This one will give you rho to the n minus 2. These two together will give you rho to the n. This one will give you rho to the n minus 2. So there are only two powers of rho that show up here. And as a result, when you try to move the powers back to the same value, you will end up with coefficients Cn plus 2 and Cn being related to each other. A standard two-term recursion relation which will make life a lot easier in the long run. So this is the equation which we would much rather handle using a power series or power series like method rather than this original equation that you had for capital R. Note that although I had started out saying power series as a means of solving this equation, I amended myself a bit in the last sentence and I said power series like. And of course all of you know the reason. Rho equal to 0 being a singular point, you cannot really have a power series solution to the equation about rho equal to 0. So at least you can't expand a solution to this in powers of rho minus 0 only. However, because rho equal to 0 is a regular singular point, we know that the solutions are essential singularity free and hence we can try a Frobenius type solution. So basically what we do is we don't take a power series, but we do take a form which looks like this. C nu rho to the nu plus s is the presence of this rho to the s, which essentially tells you that this may differ from a power series. If s is negative, of course, the solution will have a pole at rho equal to 0. If s is fractional, it will have a branch point. Of course, it's possible that s is 0 or a positive integer, in which case that particular solution will be free of a singularity at rho equal to 0. Because rho equal to 0 is a regular singular point, we do expect both solutions to be free of essential singularities, but we do expect that there has to be a singularity at least in one of the two solutions. So even if one solution is free of singular behavior at rho equal to 0, the other solution will definitely behave badly there. Our aim, of course, is to find out the solution, if it exists, which behaves nicely at rho equal to 0. Now, I will not go through the entire details of the power series solution or the Frobenius method. You all know what to do. You just take the power series C nu rho to the nu plus s, a LoRa series to be more precise, and then differentiate it term by term and plug it into the differential equation. If you do all that, what you will get ultimately, after you do a lot of simplification, is a sum like this. You have a rho to the nu plus s minus 2 term, which essentially comes from this one, and this one, and you have a rho to the nu plus s term which comes from this term and this term. We have just combined them all together and written them in this particular fashion. Now, of course, the next step would be to rewrite everything so that you end up with the same power. So rho to the nu plus s. So you have to move this nu to nu plus 2. And that's what you do here. Here all the nu's have been changed to nu plus 2. So this nu plus s has become nu plus s plus 2 and so on. And what is important is that the limits have to be changed. the limits now go from -2 to infinity. You have done nothing to this term because this was already at rho to the nu plus s. Now we combine the two power series together, and of course you can only combine them in the common region, that is from nu equal to 0 to infinity, which is there in both the sums. But the first piece here actually has two more terms, and these two terms give you two extra pieces which do not combine with other terms in a recursion relation. So what you end up with ultimately is a nu equal to 0 to infinity sum involving this coefficient and this coefficient, both of them together. But in addition to that, you have the nu equal to -2 term from this, which is s into s plus 1 minus l into l plus 1 c0 into rho to the s minus 2. You also have a nu equal to -1 term, which is s plus 1 into s plus 2 minus l into l plus 1 into c1 rho to the s minus 1. The next step, as you all know, is to equate each and every coefficient of this Frobenius series to 0, and that will give me a recursion relation from this piece here. But before that, we have to equate these two coefficients also to 0. Now, C0 simply cannot be 0 because C0 indicates that this is where your power series or Frobenius-like series starts. So C0 is not 0. Hence, this immediately tells us that s into s plus 1 minus l into l plus 1 has to be 0. This, of course, is what you call the indicial equation for the Frobenius method because it tells you what the index s is. By the way, the index s happens to be the lowest power of rho in this power series. And here, for values of rho close to 0, that power is what is going to dominate. So, not only is this important because it gives you the indicial equation and hence gives you the index value, which will help in the rest of the solution. This is important even if all you were interested in is the behavior of the function very close to rho equal to 0, because there rho to the s is what is going to simply dominate the whole thing. Now we know that this equation is a quadratic one, so it has two solutions, and the solutions are very easy to find out. One of them obviously is s equal to l, and the other one, which takes slight bit of more work to work out, is s equal to minus l plus 1. So the behavior of the solution of our differential equation for f, when rho is very, very small, is either like rho to the l or like 1 by rho to the l plus 1. And this should be pretty familiar to you by now. You know that rho to the l is the kind of behavior that we would like to have, not 1 by rho to the l plus 1. So this is the kind of behavior we will have to drop. So the solution we want of the two independent solutions is the one which goes like rho to the l as rho goes to 0. And since for either of these two cases, s plus 1 into s plus 2 cannot be equal to l into l plus 1, c1 has to be 0. So what is very important here is c1 is 0 by the indicial equation like equation that we have got already. And now our recursion relation, which will come from here, will give you c2, c4, c6, c8 in terms of c0. c3, c5, c7 will all be 0 because they are related directly to c1, and c1 is 0. So the final series will take the form rho to the l times c0 plus c2 rho square plus c4 rho to the 4 and so on. I am sorely tempted to say even powers of rho only, but actually remember L can be either even or odd. So depending on whether L is even or odd, you have either even powers only or odd powers only. But what is important is that apart from the overall rho to the L factor, you end up with only even powers in this series. The next step in solving the problem, of course, is to find out the relationship between the coefficients, and that's straightforward. You just equate this coefficient to 0, and that will immediately tell you that c nu plus 2 is basically this expression, 3 plus 2 into nu plus l minus lambda by nu plus 2 into nu plus 2l plus 3 times c nu. So this will give you c2, c4, c6, c8 in terms of c0, and that will help us build up the entire series. So this should really not be a problem at this stage, except that we already know that this infinite series has a potential for trouble. Remember, this infinite series describes a function capital F, and we do know that capital F may very well diverge like it is a rho square. And in fact, if you want to check whether this diverges, you should look at high powers. And if you investigate the C nu plus 2 by C nu ratio, which turns out to be 2 by nu for large nu, it's a simple matter of just taking the large nu limit of this expression, you can easily show that this diverges like it is a rho square. This should not come as a surprise, because we did know beforehand that f of rho can behave like it is a rho square for a very large rho. So we need to handle this problem by the same means that we have used so far. We will prevent this series from being an infinite series. That is, we will truncate this series. But before we do that, let me just point out that although this equation is for any nu, we are only interested in the case where nu is twice n, where n is some integer, because only even coefficients will appear in your final answer. So just by putting in nu equal to n, you can write this in the form C2n plus 2 is, well, this is just exactly this expression with nu replaced by 2n. This of course gives you the relationship between C2n plus 2 and C2n, and n of course takes values 0, 1, 2 and so on. So if you want to truncate, you want to essentially ensure that C2n is not 0, but C2n plus 2 is 0, which means that there has to be some n, let's call it nr, such that for n equal to nr, this ratio here vanishes. That means lambda, which is twice e by h cross omega, remember, has to be 2 times twice nr plus l plus 3. Where nr, of course, just tells you which n value is it after which the series stops. So nr can take 0, 1, 2, 3, such values. Just by rewriting this a bit, you can get the expression for the energy. E now will depend on two parameters, nr and l, and just by simply manipulating this equation, you end up with h cross omega times twice nr plus l plus 3 by 2. Just for contrast, let me just write down below this the expression that we had obtained earlier using Cartesian coordinates. That was h cross omega nx plus ny plus nz plus 3 by 2. So ultimately, you should realize that you are going to get the same set of energies from both the expressions. Of course you should. This is the same problem, you're solving them using two different coordinate systems. This nx plus ny plus nz combination, this is an integer, a non-negative integer. Twice nr plus l is also a non-negative integer. And it's pretty easy to see that all non-negative integers can be expressed either in this form or in this form. So both of these expressions ultimately predict the same energy eigenvalues. Of course, that's not enough. Do they predict the same wave functions? Well, they shouldn't. After all, Enx, Ny, Nz, the way we arrived at that, we solved the problem by first separating it out in Cartesian coordinates. So we will get a function of x times a function of y times a function of z. Whereas here, the eigenfunctions will be a function of r times specific functions y, lm of theta phi. And it is very, very unlikely that you will end up with the same set of wave functions in both cases. So how can you have two different sets of wave functions depending on your coordinate system? The answer to that is rather easy. You have to realize that once the energy eigenvalue is degenerate, saying that this is the wave function or eigenfunction corresponding to this energy eigenvalue no longer makes sense. For a degenerate energy eigenvalue, the corresponding energy eigenfunction can be the ones that anybody has listed down, or could be any linear combinations of them. And it will turn out, as you can easily check at least for the smaller values of n, the spherical polar coordinate versions can be expressed as linear combinations of the Cartesian coordinate wave functions or vice versa. But let me just quickly show you that at least the degeneracy count matches in the two cases. So how do you calculate the degeneracy of energy levels? Let's first do it using the Cartesian method. Well, in the Cartesian expression, of course, E nx, ny, nz is simply h cross omega nx plus ny plus nz plus 3 by 2 as we said. So depends on this quantity n and n only. So the question is, for a given n, which fixes your energy level, how many possible values can you have for nx, ny and nz? Of course, once you have fixed n, nx can take values from 0 all the way up to n. It can't go beyond, because ny, nz cannot be negative. Well, for each nx, ny can take values from 0 to n minus nx, simply because ny plus nz is n minus nx, and nz again cannot be negative. Of course, once you have fixed nx and ny, nz gets fixed by that. So there is no further choice in nz. So how many different choices do we have? The easiest way to figure that out is, for a fixed nx, the number of different ny values possible is n minus nx plus 1. The plus 1 because 0 is also being counted. So basically all you have to do is add up this quantity n minus nx plus 1 for all values of nx going from 0 to n, and that will give you the number of different triplets nx, ny, nz for a fixed n, which is also the number of different independent wave functions for a fixed n. And this sum is really very easy to work out. Takes class 12 level algebra, and you can easily show that the number of different energy eigenfunctions that you can have for a particular energy level given by this n is half into n plus 1 into n plus 2. Now what about the spherical polar version of the same calculation? In the polar form, energy depends on twice nr plus L. And of course, twice nr plus L is a non-negative integer which we can call n. As I've said before, both versions give you the same possible energy levels. What about the degeneracy count here? For a given n, nr can take values which go from 0, 1, 2 all the way up to the floor of n by 2. Right? Because if n is even, it goes to n by 2. If n is odd, it goes to n minus 1 by 2. Okay. Now the important point is, for each nr, L takes a very fixed value, n minus 2 nr. There is no possibility of any further change after that. In the Cartesian version, even for a fixed nx, ny had choices because the slack could be taken up in nz. Here the energy depends only on nr and L, so once you fix nr, L gets fixed. However, what you must remember, that although it does not appear in the energy expression, the wave functions depend actually also on another quantum number, ml, and ml takes values from minus L all the way up to plus L. That means it takes twice L plus 1 different values. So basically what you do to count the degeneracy is how many different nr, L, ml values for a given n are available. That is, of course, the degeneracy count this way, and that means you have to sum up over nr, from nr running from 0 all the way to the floor of n by 2 of this quantity, which is twice L plus 1 basically. And I will leave this to you as an exercise to show that if you were to calculate this, you get exactly the same expression, namely half n plus 1 into n plus 2, as in the Cartesian version of doing things. Now that we have found the energy levels and their degeneracies, and also described to you how to work out the wave functions, let us take a step back and take a deeper look at the mathematical details of these wave functions. We are not going to go into very great details here, but we will definitely meet a few new functions which are going to be very useful in the days to come. So, first, let me point out that the radial wave function for this particular problem is related to a special function, the so-called associated Laguerre polynomials, in particular for this case. In fact, the associated Laguerre polynomials are special cases of a more general class of special functions which are of immense importance in physics. They're the so-called confluent hypergeometric functions. And these confluent hypergeometric functions are solutions of a differential equation called the confluent hypergeometric equation. The confluent hypergeometric equation, CHE for short, is a second-order linear differential equation which is characterized by the fact that it has a regular singular point at 0 and an irregular singular point at infinity. Now this should ring a bell. After all, our differential equation, the one we have been solving by the Frobenius method a while ago, exactly has this behavior. A singular point at 0 and an irregular singular point at infinity. Now the standard form in which the confluent hypergeometric equation is written down is the following. This is x times the second derivative of y plus c minus x dy dx minus ay equals 0. So these are the two parameters that you use in the definition of the equation. One is a, the other is c. And of course the solutions depend on these two parameters. As always, behavior of the solution close to the singularity, in particular the singularity at x equal to 0, is of special importance. And we can easily figure that out from the indicial equation. Or, as we have been stressing over and over again, you just need to take a look at the lowest power term that you can get from this equation. And if, say, your original solution y had extra s plus higher order terms, then the lowest order term that you will get from here is of the order x to the s minus 1. From this term also you will get x to the s minus 1. This will give you x to the s, but that's higher power, so we don't worry about that. And this one will give you x to the s, so we don't worry about that either. So these two terms will not contribute to the indicial equation. These two terms will. And it's very easy to write down the indicial equation directly from here. You will get an s into s minus 1 from the second derivative here and a c times s from the first derivative here. So the equation is simply going to be s into s minus 1 plus cs equals 0, which gives you two possible values for s. One is s equals 0 and the other is s equals 1 minus c. So at least one solution to the confluent hypergeometric equation will be a perfectly nice regular solution. This is the one where s is 0. We can actually write down the two solutions in general in this particular form. One solution will be the one where the series really starts at x to the 0. So that's C1 times a confluent hypergeometric series, which is written 1f1 a comma c semicolon x. Now here a and c are obviously the parameters that describe the function. X is the argument, of course. 1f1 is a notation which actually is used because, well, there are other generalizations to this, in particular the hypergeometric equation, which is very special and very important also. But we are going to talk about that later. It so turns out that the other solution to this equation can also be written down in terms of 1f1. I'm not going to show you the details here. Maybe I will set that as an assignment. The other solution has an x to the power 1 minus c, as the indicial equation told us, times a series which starts from x to the 0. This one happens to have a minus c plus 1 and 2 minus c as parameters, of course for the same argument x. And you have two arbitrary constants, c1 and c2, and these two together give you the entire solution in general. Before we go any further, let me first write down for you what the confluent hypergeometric series 1f1 a comma c with x as an argument looks like. So if I write that in a compact form, it looks like this. It's a series which runs from n equals 0 to infinity, and you have z to the n by n factorial as, say, in the exponential function. But in front of that, you have gamma a plus n by gamma c plus n. And this has an overall factor of gamma c by gamma a outside. Now, the presence of these many gamma functions might make this look a bit unfamiliar and complicated. However, if you remember that gammas have this very nice property that n gamma n is gamma n plus 1, then the terms in the series really become very, very simple. If I were to write this out in full, this would look somewhat like this. For n equals 0, of course, you have gamma a by gamma c here, cancelling the gamma c by gamma a here. And z to the 0 by 0 factorial is, of course, 1. So you have 1 to begin with. The leading term here is 1. And of course z to the 0 starts at 0th power, as the initial equation told us, then we will have the term for n equals 1. That of course gives us z by 1 factorial. But gamma a plus 1 by gamma a is simply a, gamma c plus 1 by gamma c. In the denominator is simply c. The next term, well, z square by 2 factorial. You have gamma a plus 2 by gamma a, but that's simply a into a plus 1. And in the denominator, you have c into c plus 1. It's easy to see that the next term will be a into a plus 1 into a plus 2 by c into c plus 1 into c plus 2 into z cube by 3 factorial. And the series will continue in this fashion. So the series really is rather simple, and it's only the presence of the gamma functions which is making it look perhaps a bit more intimidating than it should be. Now, one general statement can be immediately made from the form of this equation. If c were a negative integer or 0, this series simply cannot be a decent solution because it has coefficients which will diverge. In fact, you should have noted that if you look at the general solution, a negative integer value for c or a 0 value for c would have led to a problem anyway, simply because if there had been no problem with the confluent hypergeometric series for such a situation, then x to the 1 minus c would be a positive power of x, and so both the solutions would have ended up being regular at x equal to 0, which is impossible, as you well know, since x equal to 0 is a singular point of the equation. Now, it so happens that even the first solution, which is apparently the nicer one, actually blows up for c equals 0 or a negative integer. Now, there is a way to rescue this particular solution in that case by taking appropriate limits, but we are not going to spend too much time on that. We will actually be more interested in the special situation where a happens to be a negative integer or 0, or rather when a is equal to minus n and n takes values 0, 1, 2, 3 and so on. It's pretty easy to see that in such a case, this infinite series for the confluent hypergeometric series actually truncates and becomes a finite polynomial of degree n. And this is the situation which gives rise to some very interesting polynomials which are quite useful. Now, the most general case for that is the so-called associated Laguerre polynomial, which is defined to be essentially the confluent hypergeometric series 1f1 in the special case where a is minus n, a 0 or a negative integer, and c is a positive integer 1, 2, 3 and so on, written in this particular form m plus 1. Apart from an overall factor of n plus m factorial by n factorial times m factorial, this confluent hypergeometric series in such a situation exactly gives us the associated Laguerre polynomials, which are of great importance in many physical applications. In fact, this notation is also used when m is not an integer. So all you have to do there is change the factorials in the front to the appropriate gamma functions. Remember, whenever a is a negative integer or 0, the series becomes a finite polynomial, and that finite polynomial is called the associated Laguerre polynomial. Now, another special situation arises when the argument used is not x but x square, and c happens to be either half or 3 halves, with of course a being equal to minus n and n taking values 0, 1, 2 and so on. As you can see from the equation written down, this situation gives rise to the Herrmite polynomials h2n and h2n plus 1 for c equal to half and c equals 3 by 2 respectively. This actually shows that there is a deep connection between the Laguerre polynomials and the Herrmite polynomials. They are, after all, both special cases of the confluent hypergeometric series. So the obvious question that will arise at this stage is, what exactly is the connection between this confluent hypergeometric equation and its solutions that we have been talking about and the equation that we are really trying to solve, which, let me remind you, is this one. The equation that we get when we try to solve the radial equation for a simple harmonic oscillator in 3 dimensions. Now, let me point out that this equation has a regular singular point at rho equal to 0 and an irregular singularity at rho equal to infinity. This is exactly the same singularity structure as for the confluent hypergeometric equation, and this indicates that there should be some connection between them. The connection can be made clearer by carrying out a few manipulations, which we are going to discuss in the following. The manipulations are also not quite arbitrary. Note that we know that this particular solution f has this behavior. When rho is very close to 0, it behaves either like rho to the L or 1 by rho to the L plus 1. So this is the indecisional behavior or dominant behavior for small values of rho. On the other hand, we know that in the general solution, the way the confluent hypergeometric equation behaves, if the independent variable were called rho, would have been either rho to the power 0 or rho to the 1 minus c. Of course, the solution for f that we want goes like rho to the L rather than like 1 by rho to the L plus 1. With this in mind, what we will do is we are going to carry out this change of variables, replacing the dependent variable capital F by the dependent variable capital G, connected to f by this particular relationship. And since f, the one we want, goes like rho to the L, G should have a solution which goes like rho to the 0, which, remember, is the same behavior as a confluent hypergeometric solution series has. So we would be rather optimistic that G would be related to the confluent hypergeometric series. So let's try to see what happens when we do this change of variables. I'm not going to show you the details of the algebra here because this is again something you've done many times before. If you just were to carry out the substitutions, change the variables properly and carry out the algebra a bit, this is the equation that you are going to get. This of course ends up looking substantially simpler than the original equation, especially because the L into L plus 1 by rho squared term, the dominant term at rho equal to 0 in the original equation, has gone away now. And that should be sort of obvious because what we have done is we have ensured that we get an equation now which behaves much more mildly at rho equal to 0 than the original capital F did. And this lambda minus 3 minus 2L, let me just remind you, turned out to be equal to 4 nr according to our quantization conditions. So we expect this to have a finite polynomial solution when this quantity is given by 4 nr. Now this equation is still not exactly in the form of the confluent hypergeometric equation, so we are still a bit far away from our goal, but we can get there pretty easily. All we need to do is do a simple change of variables, and that change of variables is rho square is to be replaced by z. Remember, rho takes only positive values or rather non-negative values from 0 to infinity. So replacing rho square by z is a 1-to-1 transformation, so not a problem at all on that score. Moreover, rho being z to the half means that since g behaves like rho to the 0, at least one solution for g behaves like rho to the 0 when rho is very small, that solution will behave like z to the 0 when z is very small. Now this change of variable actually achieves what we want to do, because as you can easily verify after a bit of trivial algebra, and I do urge you to verify it for yourself, the equation that g obeys turns out to be this one. Z d to g dz2 plus L plus 3 by 2 minus z times dg dz plus nrg. Let me just compare this with the confluent hypergeometric equation which is here. If you compare the two, you will see that this exactly is a confluent hypergeometric equation with c equal to L plus 3 by 2 and a equals minus nr. Note that we already have learned that we get well-behaved solutions when nr is either 0 or a positive integer. That is, when a is either 0 or a negative integer. This is exactly the situation which will give rise to the confluent hypergeometric series getting truncated and ending up being a finite polynomial. In particular, the finite polynomial that we will get is the associated Laguerre polynomial corresponding to L plus half. Remember, there in the Laguerre polynomial definition, C was actually M plus 1. So, our G, the well-behaved G, is the associated Laguerre polynomial of order nr, comma L plus half. By the way, this L plus half is written in brackets, but you should not confuse this with the often used notation where this indicates L plus half times differentiation. Of course, L plus half being a fractional number, that doesn't really make sense directly. This particular Laguerre polynomial is exactly what your solution is. So our radial wave function turns out to be a constant times e to the minus rho square by 2. Remember, this is the factor we put in at the very beginning to take care of the behavior at infinity. Times rho to the L times the associated Laguerre polynomial Lnr, L plus half of rho square. Now the Laguerre polynomial actually happens to be very, very important for us because we meet it here for the three-dimensional harmonic oscillator, but also because we are going to meet it again for a solution to the Kepler problem, or as it is usually known, the hydrogen atom problem. Now, it is also not surprising that the Laguerre polynomial is something which appears in this particular context. You might wonder where the Herrmite polynomials have gone, because those are the ones which really appeared in the solution for the one-dimensional harmonic oscillator. But let me point out that they actually belong to the same general class, the class of confluent hypergeometric series, in the special case when the series truncates and becomes a polynomial. The spherical harmonic oscillator is not the last situation where we are going to meet the associated Laguerre polynomial. In fact, the associated Laguerre polynomial is going to play a big role in the very next problem that we are going to solve, which will be our last preliminary lecture before the formal coursework for this semester starts. And that problem, of course, is the hydrogen atom problem, which is, after all, a two-body problem. We will first show you how you can follow the same lines as you had done earlier for classical mechanics to reduce this to a single body problem of a single particle moving in a central potential, and then go on to solve the radial equation. For that, we will see that the Laguerre polynomial will again show up in that particular solution. But that is for the next lecture. Until then, bye.